This conference will now be recorded.
Hello, good afternoon, good morning, good evening, or good night, wherever you're joining us from. It's a pleasure once again to host you in a Smart Otanyemi webinar. The topic for us today is EBUS, the global language for energy, and it's a joint collaboration between two wonderful innovation ecosystems on energy, one being EBUS and the other one Smart Otanyemi. My name is Sami Kasi. I'm a research team leader at VTT, the Technology and Innovation Powerhouse of Finland. I will be your host today. Joining me today is my colleague Sanna Örni. She's the Smart Otanyemi co-creation manager. And then joining us from the EBUS side, we have Niklas Arpula and then Mark Helfter. And we will guide you through a couple of presentations. If at any point you have any questions, please look for the chat bubble, which you will see in your application. Please type in a question, send it to me, and I'll be asking the presenters along the way. What I will do is that at the end of each presentation, maybe, ask a couple of questions, and then towards the end, we will try to reserve some time for further Q&A. Just to let you know, we have started everybody in a mute mode. This is just to ensure we don't get too much noise disturbance. However, the chat channel is open, so please do key in any questions at any time which you may have. And to start forward, I'm going to hand over to my wonderful colleague, Sanna Örni, to say a few welcome words and then to also tell you a bit more about Smart Otanyemi. So, Sanna, floor is yours.
Thank you, Sami. Good afternoon, everyone. It's my pleasure to open this Smart Otanyemi webinar today. It's great to see so many participants online at the moment. What is Smart Otanyemi? Smart Otanyemi is an innovation ecosystem focusing on smart energy solutions that are both sustainable and commercially successful. Our roots are in Finland, the country up in the north in Europe. We connect experts, organizations, technologies, and pilot projects in order to create world-changing ideas for future smart energy. In Smart Otanyemi, we strongly believe that collaboration is the key to success when you want to address challenges that are too complicated for anyone to solve alone. The topic of today's webinar is EBUS, the global language of energy. So now we have chance to hear and see more, as we have honor to invite Mr. Niklas Arpula and Mr. Mark Helfter to give their insights and experiences of EEBUS Initiative. So let's move on. The stage is yours. I wish you a pleasant and insightful webinar.
Thank you very much, Sanna. And Niklas, let's now move to you. Matthias will be giving you control over the screen, so you can load your presentation over there. And all of you who have joined, we would like to let you know that we are recording this webinar, and we will be sharing a recording with all of you later on via link, so just please stay tuned for that. Niklas, floor is yours. Thank you.
So, thank you, Sami. Thank you, Sanna, for the introduction. Welcome also from my side following this EBUS webinar, and greetings from a cloudy Cologne. And thank you to everyone for the interest to hear more about EBUS. So my name is Niklas Arpula, and I represent Kio, a Cologne-based software company specialized in EBUS software solutions. So, the EBUS standard is represented and developed further by the non-profit organization EEBUS Initiative and its members. Here in the overview that you hopefully can see, Can you see utilities, HVAC manufacturers, EV charging infrastructure providers, software companies, small and large, as well as industry associations, such as the VDA representing German automotive OEMs, also the German heating industry and the leading technical regulator, VDE, support EBUS. And for all the members is standardized and interoperable communication over energy relevant and seen as a key business element. Of course, without forgetting the higher mission to enable the energy transition to a greener future through increased energy efficiency and self-consumption. And this is the reason why all these members are committed to develop jointly an interoperable language for energy. The real work of the initiative happens in the working groups for various domains. Here the members bring their ideas and market requirements into the use case definition process. These requirements are then transformed into high-level use cases describing energy-relevant device communication, but firstly from a business perspective. And the members work together with the goal to define these use cases so that they meet the expectations of all involved companies. This process is sometimes maybe slow and contains many iteration rounds, but only so can a joint understanding be reached. And no member can push their idea through without the consent of others. So what is an use case? An EBUS use case defines, for example, how an EV charging station should communicate with an energy management system in order to optimize the use of self-produced solar energy, or how the energy management system should communicate with the grid in order to support peak shaving. In the next phase are the high-level use cases transformed into detailed use case specifications and data models. And based on these specifications, can members start to implement an interoperable EBUS solution. The verification of the implementations is done in so-called plug fests. And if they are successful, are the products ready for series and specs for release? If not, is the implementation as well as the specification reviewed? The finalized and released specifications are free for anyone to use, also non-members, and without any cost. The initiative collaborates with other IoT alliances also to enable globally applicable use case implementations. So only what the industry needs flows into specifications, means only use cases that really have a value for the members and end users are defined. The EBUS data model is called SPINE, and it is used to describe the technical implementation of an EBUS use case. This data model is standardized by both Senelec and ETSI. SPINE is independent of the transport layer and can be transmitted with many technologies, so mapping to other protocols such as Modbus is possible. SHIP is the EBUS native communication protocol for TCP/IP environment, but many other solutions are also possible, for example, for UDP environment. To ensure a maximum flexibility is the EBUS solution architecture based on the Smart Grid Architecture model SGAM, maybe familiar to some listeners. And this assures that changes on one layer do not require a revalidation of the entire EBUS solution. So EBUS sets the basis for interoperability in the energy domain by defining specifications for the three middle as GAM layers: function layer, information layer, and communication layer. So the use case specification is the guideline how to use the SPINE data model for building the use case specific EBUS application. The SPINE specifications, so resource and protocol, describe the device resources and how to create connectivity between EBUS devices. The SHIP specification defines how this SPINE content can then be transferred between EBUS devices with the TCP/IP technology, how devices find each other, and how the communication is done in a secure way. So the SPINE data model should be seen as a toolbox and the use case specification as an instruction how to build an EBUS conform solution. It is of course important to highlight that the exact application using the EBUS data is realized by each implementing party by themselves according to their business model. EBUS is not standardizing energy management, but the necessary communication interface. So let's have a look at the current drivers behind EBUS. What is happening out there in the grid and the buildings? So the power system is in transition, and the production of electricity is moving from central to decentral, from controllable fuel-based energy generation to volatile sources such as sun and wind. Moreover, the increasing electrification of heating and mobility drives electricity consumption up. So we have a lot of EVs and heat pumps coming into the system. What happens behind the meter is today a black box for the DSOs. So the power distribution infrastructure on grid and property level is not dimensioned for this new demand. The consequence on building level is, well, the main fuse strips, you have a blackout. Or the blackout happens in the local distribution grid due to the fact that the transformer on the street corner is not dimensioned for this new demand. The consequence is, however, not only a blackout, means lights out, but also that the comfort promises of the energy supplier, DSO, device and service providers cannot be fulfilled. Means no electricity, no battery charge for the 80k EV, neither hot water or clean laundry. Means they have to offer a solution that enables to avoid this problem. And the conclusion is that energy management is necessary to balance demand and supply on building level. So what are the EBUS goals? Besides that they create specifications for use cases and data models on behalf of the industry. Only with connectivity between single devices and the EMS can an holistic approach for managing the energy flows be realized. Optimization of self-consumption of energy and cost shall not lead to loss of customer comfort. And the communication interface to the grid must be digitalized. For the device and energy management providers enables connectivity based on standardized use cases and data models the possibility to offer complete solutions for the customer instead of single devices that cannot offer the connectivity what the customer demands. And relying on proprietary solutions controlled by global IoT platform providers, on the other hand, would put the entire business model in danger. So EBUS provides a democratic and future-proof framework for this connectivity. One further aim is to make networking of energy-relevant devices and systems plug-and-play ready. This means as easy as connecting Bluetooth devices. The more complicated and the more brand-specific lock-ins exist, the higher is the hurdle for the customer or installer to engage with an holistic approach. This EBUS approach is, of course, scalable from single-family residential houses to multi-tenant buildings and commercial buildings as well. So the EBUS solution for bringing demand and supply in the building and with the grid in balance is based on two cornerstones. First, the energy management is in center. A holistic approach to include all devices is a must. An active management of demand and production. The increase of self-consumption and taking use of the flexibilities the devices offer, from making hot water to rescheduling intelligent washing machines. And learning from the individual demand profiles of devices and users. And making energy forecasts based on historic data. The second cornerstone is providing an interface to the grid and thus to enable use cases for energy transparency to the grid or tariff optimized operation of devices. And last but not least, capacity management on the grid connection point. Now, let's have in the next slides a closer look at some of the use cases mentioned. The EBUS solution for capacity management on the grid connection point looks following and is based on existing EBUS use cases. So the DSO, or the one responsible for managing the local grid, provides a power limitation signal to the digital grid connection let's say the smart meter, or here in Germany, device could be the smart meter gateway or the control box. On this device, the power limitation signal is mapped from, for example, IEC 61850 or OpenADR to SPINE and handed over to the local EBUS-based energy management system. The EMS manages the local EBUS devices behind the meter, in other words, decides who gets how much electricity and when, and reduces their consumption if necessary to stay below the given limit value on the grid connection point. How the EMS application and controlling algorithms are implemented is up to each EMS vendor themselves. So despite the grid setting the limits for load at the grid connection point, enables this approach an efficient local use of energy with minimal impact on consumer comfort by using the EMS as the orchestrator of energy behind the meter. Noteworthy is also that this approach does not exclude market-driven optimization across building boundaries using, for example, cloud-based artificial intelligence. The power limitation sets simply boundaries to this optimization. Another use case regarding interfacing to the grid is tariff-optimized operation, or maybe better is to say interfacing to the market. So in this use case, the EMS receives incentive tables which it distributes further to the EBUS devices in the building. Based on the incentive table and device energy demand takes a negotiation place, and as a result is a consumption plan set. Based on this consumption plan, controls the EMS and the devices. And if incentives or demand changes, is a new negotiation triggered. In the graph on the right side, the red line shows the connection capacity with a limitation at peak hours, whereas the colored areas show energy cost over the day. The darker, the more expensive is energy. So the market defines the cost of energy and the DSO sets the limits to the available capacity. But with the EMS, can the consumer optimize cost by having the devices run at the time of lowest cost? On building level, EBUS enables an increase of self-consumption and autarky and the visualization of energy-relevant information, thus saving the consumer money and providing insights on energy use. This information on the EMS can of course also be shared with a smart home system. For this picture are several use cases developed, but there is always the EMS as the central element with communicating with single devices. Keeping the EBUS solution to capacity management in mind, let's have a look at the current legislative and regulatory discussion here in Germany. So to avoid extensive grid reinforcement, is it planned that the grid connection capacity will for the energy consumer be divided into guaranteed and conditional capacity? Contrary to today, would the full capacity of the grid connection point not be at all times available? And the DSO could reduce the capacity to the guaranteed capacity, which is 5 kilowatts in today's discussions, if necessary to avoid grid overload. Thus, consumers with high demand but no flexibility have higher grid connection costs, whereas consumers with flexibility in their private energy system, means heat pumps, EVs, storage or PV systems, would pay less. Again, only an energy management system can orchestrate the energy flows in the property with least impact on comfort and cost. So now my apologies for the German language content, but last week the National Platform for the Future of Mobility, this is the organization representing the German government when it comes to mobility strategy, released a report and roadmap for intelligent load management on the grid connection point. Means how to enable load management in the low voltage grid for DSOs. The in 2020 to be realized first version of the requirement specification for the digital grid connection point will include EBUS as the first technology for this interface. In the first step, this concerns the control box, here called Steuerbox, controlled by the DSO to control the resources behind the meter. And this is the reason why, for example, at this year's Energy Industry Fair eWorld in Essen presented several smart metering providers EBUS solutions together with other grid stakeholders. And this all despite the still ongoing regulatory and legislative processes. Of course, parallel to the national activities in Germany is the approach being brought also to CENELEC and IEC and their relevant technical committees and bodies. Distribution grid capacity challenges are, of course, issues not only limited to Germany. This is a problem concerning most power distribution networks, and therefore is the EBUS approach also included in international projects. One very interesting project is the Global Grid Integration Project, where, for example, major automotive OEMs, both European and US, work together with DSOs, EMS and charging solution providers to develop solutions for global interoperability between charging infrastructure and the distribution grid. Here, EBUS is used for energy and load management in the private and semi-public domain, whereas OCPP is the protocol for public charging and billing relevant issues. In the project scope is the EBUS solution for local load management and grid interaction being tested and developed further with both IEC 61850 as well as OpenADR architectures. Also, use cases for self-optimization and tariff-optimized energy use are included. The plug fests have so far been successful, and hopefully can the next steps, unfortunately halted by the corona crisis, be soon taken again. So EBUS brings energy management and comfort, typically associated with the smart home, together. Often this smartness has, however, very little with energy efficiency to do. By using EBUS, can the device manufacturers provide smart home connectivity based on a standardized interface instead of relying on proprietary platforms where they risk to lose their data sovereignty. And just as in the grid use cases, acts the EMS as a link between the two sides and enables thus a truly smart home. As an outcome, can all stakeholders offer more value to the end user? So then a bit about standardization and interaction with academia, for example. So as I earlier mentioned, is the EBUS data model spine standardized? Here you can see the actual releases. Of course, is further standardization ongoing with national and international standardization bodies. The interesting standard on the right side is the Tariff for inner ontology, to which the EBUS data model spine is fully conform. Tariff is an ontology initiated by the European Commission and currently also strongly pushed by the Commission. The reason is that in order to realize the energy system transition to green and decentral production must it be digitalized. This can, however, be done to the fullest only with sufficient interoperability all the way down to single devices in the building. Here are common ontologies beneficial. One data model will never rule the world, you can say, but the more data models are based on the same ontology, the easier it is to harmonize the data interfaces and map content between systems. Which takes us to the Interconnect Project. This is a large energy innovation project funded by the Horizon 2020 program, and surely something interesting for the smart Otanyemi ecosystem, at least prospectively. The goal in Interconnect, with more than 50 partners and pilots in 8 countries, is to develop interoperable connectivity from device to grid level that enables balancing of grid, decentralized energy generation, storage, and flexible energy requirements for devices. And this is to be done by developing the Tariff ontology further and by bringing Tariff for inner or spine into as many solutions as possible, to tariffize everything, so to speak. So I'm closing to the end of my presentation. The collaboration between existing standards and harmonizing the interfaces to other domains is the key to bringing the smart grid and the smart building in sync. And when it comes to energy, is the EMS the central element in the building, and EBUS covers thus already today the change from the grid to the EMS and further to the EV itself. And by collaborating with strong partners such as the VDE and VDA, has Ebus built a scalable and future-proof solution that meets the needs of both industry and users. And the commitment of these globally active OEMs, such as the Volkswagen Group and device manufacturers, is indeed the proof of this, which will actually be nicely demonstrated in the next presentation by Mr. Helfter from Haga Group. So I'd like to thank you for your attention, and please do visit the Ebus website for more information and the release specifications. Of course, I'm also happy to support you in any questions surrounding Ebus, and I'm also happy to discuss in Finnish if you prefer that instead. So thank you very much.
Thank you very much, Niklas. Let me start off with a couple of questions before we move on. First and foremost, why EBUS, and what was the triggering moment to get it all started?
So the EBUS roots lie actually in a German, how should I say, a German development project in I think it was 2009, called Smart Watts. And there came the first ideas to develop a language for energy. And quite quickly it became clear for the involved ones that there has to be an initiative that pushes EBUS, and in 2012 was the EBUS Initiative founded with a handful of companies. Kio was actually one of the founding companies there, and since then there's happened a lot. There is a lot of members, and EBUS is really the preferred solution for the OEMs, for the grid actors, and that is, I think it's a very excellent development.
Yep. And then another question. I mean, you were showing, let's say, that EBUS can be used across industrial sectors. I mean, you have, for example, the vehicle industry. You are talking also about buildings, for example, the built environment per se. And my question here is that, how does the standard actually work across these industries? And is there some form of mapping or interface with, these different industry standards?
So where EBUS is focusing is to define use cases and data models relevant for energy in the building and interfacing the building. So the focus is on energy management.
Right.
And the energy management system is then the central element through which you can realize mappings to other technologies. If we now look at this picture. So the EBUS intention is not to rule the world. I think one standard, one data model cannot do that, and that's why it is important to harmonize the interfaces to the already proven and widely spread solutions.
Yeah, and let me just take one more final question before we move on. And for all of you participating online, you will see this chat bubble on your screens, in the GoToMeeting screen, that is. So please click on it and send us any question you may have at any time, and we will be taking some of them during after the presentations and then towards the Q&A in the end. So Niklas, one final question before we move forward. In one of your use cases, you talked about how EBUS would interface and actually make the smart home more attractive and more user-friendly and everything. And here the question is that how would it work within existing networks and in particular devices? So do we need, as consumers or building owners or operators, to make any changes to our devices, or as to how and when we use energy within our facilities?
So at the end, the interface connecting the smart home and the energy management would be the interface on the energy management system. So the energy management system provider can provide in his solution an interface where the smart home platform can connect. And what happens between the EMS and the energy relevant devices is controlled by the application of the EMS. So at the end, the users of these devices here don't have to change anything. It's about an agreement that the EMS provider offers an interface to one of the widely spread platforms, which is of course already today happening by some providers.
True. Very good. Thank you so much for getting us all excited about EBUS. But now let's move forward. Matthias, if you could give the control now to Mark. So we'll now have Mark Helfter from the Hager Group, and Mark will be guiding us through energy management and presenting an example of the Audi E-Tron and the Hager philosophy. So Mark, floor is yours.
Yes, good afternoon, everybody. So I hope you can see my presentation. I put it in full screen. Should work now. Yes. So everybody can see my screen. My name is Mark Helfter. I'm in charge of innovation in the Hager Group. Hager is a 2 billion German company. And Hager is is a solution provider for electrical installations and distribution in buildings. These are our roots. And today, today I will explain you what we did with Audi to enable smart charging with the new Audi E-Tron. So the Audi E-Tron is a car that has been launched now last year, 1 year in the market. It's a high range car, and what is interesting here is that this compatibility will, or this smart charging will work not only for the Audi, but will also work for the next coming Volkswagen ID car, and generally speaking for all the car having the ISO 15111 standard implemented. And this will be deployed massively on all electric cars in the, it will start this year, and in the 2-3 next coming years, all cars will have this ISO 15111. It's a high level communication called also feature. So what is the target of Audi? The target of Audi is to have a flawless integration of the car in the electrical ecosystem. The car should not be a source of trouble for the network, for the building. And that was the main target of this project. It was also, of course, to charge your car in a sustainable way, avoiding CO2, and also taking care of the economical aspect. So for this, we are not supplier of Audi. We did a collaboration. That means Audi has worked on his car to make it able to discuss with our device, which is an EMS or EMC, energy management controller. And these two features bring added value to the end customer. And this added value is, so this is the way it works. So we have communication between the car and the EVSE, the electric vehicle supply equipment or charging station. So here we use ISO 15118, and then we have a communication between this charging box and our controller via EBUS. And the features or the solutions we offer are these three main functions. The first one is blackout avoidance. So this is to avoid that you have a shutdown because you are charging your car, for example, in the evening when you have power limitation. And this is very depending on countries. In Germany, for example, there is today no power limitation, but there will be, as Niklas explained before. But if you take, for example, South Europe, I don't know the situation in Finland. In South Europe, there is a limitation. Yeah, you have an abonnement, and you have, for example, 6, 9, 12 kilowatt maximum power available. So that in the evening, when you are cooking, for example, you need a lot of power, and then you have to turn down or reduce the power you give to the car. That's the solution you have chosen. It's to reduce the power and only reduce it at this time. We could have a fixed power limitation, but then this means a longer charging time. So with a dynamic power adjustment, you optimize both the use of your electrical installation and the charging time of your electric car. Then, as I mentioned before, PV first. When you have a PV on your roof, and this becomes more and more popular, when you have PV on your roof and when the power exceeds the consumption of your building, you send the information to the car and tell him, now I have overproduction of PV, please charge. And the third one is called coordinated charging. Here there are two things. There is, on one side, there is a forecast. That means we have informations of our building. We have the power production forecast via weather forecast. If it's when you have PV, you are able to predict for the 24, 48 hours what production you can expect from your roof. The second one is forecast of your consumption. This is based on self-learning processes. We observe our building, and based on this, we can, after a learning time, we can predict what will be the consumption of the building. And when we combine both, we are able to give this information to the car, and the car can build himself his charging plan. And you know that these cars, you're able to set, for example, your daily travel. For example, I need 50 kilometers per day. And if in 2 days or 3 days you need to do 200 kilometers, then based on the weather, the car can optimize the charging of these 200 kilometers. If tomorrow it's raining, after tomorrow, if it's sunny, the car will wait on after tomorrow to put the 200 kilometers in his battery. That's the idea behind. And the other topic is dynamic tariffs. This is not yet really existing. There are a lot of plans about this. I guess it will arrive on the market in the 3 next years. Dynamic tariff is, instead of having fixed tariff as today, you get every day you get a tariffication plan for the next 24 hours, and you take this into account to optimize the control, the energy management in your building. And this information is sent to the car. So what is important here is that this system doesn't control the car. The car decides by himself if he wants to charge or not. It's more an incentive the big loads.
Nicholas, can you repeat the last half minute or so? We lost your voice for a while.
And
oh, sorry, Nicholas. Yeah, Mark. Sorry. Yeah. Yeah. So after here,
no
after you were talking about the dynamic tariffs.
Was it okay for the function?
Yes, this was okay. Yeah. So when you finish dynamic,
so dynamic tariffs
from here.
is understood. So
yes.
now okay, perfect. So what is our global vision for the future? When we speak about energy management, we think about considering the production systems, the storage system, and the main consumers in the building. When you look at the main consumers in the building, there are mainly two. There is electric car, and there is HVAC, heating or cooling mainly, depending on where you are. In northern countries, it's more about heating. And maybe you know that in 2030, all heating systems will become electric. the internal combustion heating systems will disappear in 2030. So the ecosystem of the building extends not only to the mobility, but also to the heating. The future will be electric. That's what we think, and we are working in this direction also. So we have to manage the main loads, electric car, heating and cooling systems. We have to manage storage, and we have to, let's say, manage the production. We don't really manage the production. We try to avoid shutting down the PV installation, and this is feasible. And of course, we combine this. So in energy management, there is a first step, which is optimization of the building. And that's what we are doing with our EMC, Energy Management Controller. So we can control or optimize the charging of the car, but we can also take into consideration the storage system combined to a local production when you have one. And there is also the management of the heat pump. This is now starting. More and more heat pumps will be able to speak the EBUS language and then also to speak with our controller. And the heat pump is very comparable to a car, because you can stop the heating, you can store heating. So the main difference with the car, it's not reversible. And today the cars are not reversible too, but they will be. So this is what the system looks like. And so the first step is local optimization, what I call prosumer, producing, consuming. And the second step will be services to the grid, because as you said before, Niklas, we have more and more renewables that are not controllable. So that means the flexibility cannot come 100% from the production side, but the consumer side has also to offer flexibility. And the dynamic tariffs is an example to have this flexibility on the consumer side. That means that the DSO will send information through the meter or through the smart meter gateway to our system, EMC, and he will optimize, taking into account the production, the consumption, and the tariffs he gets. He will optimize the energy profile of your building for the coming 24 hours, for example, with, of course, updates based on situation changing. Okay, so, and here, the language we can use between these different consumers or producers can be EEBUS, and is EEBUS in our scenario. What I wanted to add is that we are working currently on reversibility for electric cars, called vehicle to grid or vehicle to home. And therefore, we also use the combination of ISO 15118 and EBUS to discharge the car in the building. So that not only the stationary battery is part of the flexibility in the grid, but the car also can become an actor of flexibility in the grids. I'm trying to change my page. Okay, so here our philosophy is to use a flexible agent model. And what does this mean? This does mean that we don't control directly the systems. There is one thing we control directly, that's the storage system, because it's really our product. And in fact, the storage is there to adjust to all situation of the consumers and the producer. It's only a buffer. It's only a tool to make possible the integration of your local production and your electric car, for example. The other big consumers, electric car, heat pump or cooling system, are not controlled directly, but they get recommendations about the risk of blackout, for example. And when this arrives, the car reacts immediately. We can give tariff information, high or low. and we can give information about the PV production and the global consumption of the building. And then these devices can build their charging plan. That's what the car does today, the Audi car, and the heat pump is more or less very similar in terms of functions to a car and can do the same. In the future, we can add additional features such as where is the electricity coming from? Is it CO2 intense or CO2 free? This Pmax limitation, power limitation, can be taken into account. That means, for example, I get an information from the grid to reduce my power by 20 kilowatt, and then my EMC can search internally what is the best solution, avoiding to decrease the comfort of the user, what is the best way to get this 10 kilowatt. And we can have dynamic and feed-in tariffs. That means that we can use our car to participate to the grid flexibility and also to improve the payback of all these systems, because the car is not only there to drive, but can also generate money by selling services to the grid. So try to change my page, doesn't work. There is a long delay, sorry. So I'm through. Thank you for attention.
Thank you very much, Mark. Very, very interesting. And as you can imagine, we have some questions for you also. And at this point, we will switch, let's say, to the question and answers also. But let me throw in some questions to Mark first before opening the floor to questions coming in any direction, because we already have a few from Mark. So, Mark, just to start off with, you talked about energy management. Is this, where is it managed? Is it at a home level or a building level? I mean,
it's at the building level.
Yeah.
Yeah. So you see on this drawing, the energy management controller or energy management system is the brain of the building. So here our main focus today is residential because it's our main market, but you can do the same for our commercial buildings, of course.
Yeah.
So this is a brain in your building, and this brain is in charge of all topics related to energy. It can be, as Niklas showed it, also connected to the smart home world that is more related to comfort. But the focus of energy of EMS or EMC is really energy. That means local production, local consumption, that's today, and in the future also exchanges with the grid.
Yeah. And Mark, you already in a way responded to this question, but I mean, the question had come in as, is the Audi E-Tron capable to push electricity to the grid? That's the vehicle to the grid. And you said this is something which is possible and working on. But if I may, ask further that if we do have this vehicle to grid by the Audi, or for that matter, other cars, is it using AC or DC for that purpose?
So today, the Audi E-Tron is not able to do reversible energy exchanges.
Okay.
This is still in prototyping phase. That's the first information. I think the first cars able to do vehicle to X will be available in the 3 next years. That means 2023, between 2023 and 2025. Then the question of AC or DC, this is a bigger question than just for the reversibility, because and there are different philosophies in the market. You have OEMs working on AC, others believing in DC. The advantage of AC is that all the infrastructure is AC, so that means there is not a big revolution in the building, or let's say the fixed infrastructure. You have to do the work on the car. The advantage of using DC is that you can avoid having a lot of stuff in your car. And in the future, that's what we believe is, we are working on DC today, DC, reversible charging. We believe that in the future, the cars want to get rid of their converter, which is weight, place, and volume and money. And but this will take time. We are not ready today. We don't have the infrastructure. This will take time, but I believe that in a mid long term, the switch to DC is possible.
Yeah. I'd like to perhaps, move a bit forward, because we have, quite a bit of questions which have come for you. And first of all is that, you were talking about that the HEMS and the EMC, for example, they provide recommendations. So they don't make decisions, but they provide recommendations. Can you, in a way, elaborate a bit on that? And in particular, so who makes the decisions? Now, you mentioned that, that the information goes, for example, to the E-Tron, and that can help decide or do something over there. But does it, decide on itself with existing devices? Do we need to do something over there to, let's say, make these decisions?
So there's one thing the car reacts immediately, that is when there is a risk of blackout. So when we tell the car, please decrease the power, because if not, the building will be shut down, then the car reacts immediately. For the rest, if we tell the car that there is PV available, the car decides if he wants to charge or not. That's a strategy in the car.
Right.
So in the cars, you can define scenarios. I want to optimize CO2 free. I want to optimize economic charging. And based on this, the car will define a plan. And then there is and we get a feedback. In fact, we send recommendations and we get a feedback that are taken into account to elaborate the global energy plan for the whole building. That's the way it works.
Right. One more question, before, and by the way, anybody, if you have any questions, please do send it in the chat window and we'll pick them up as soon as they come in. So again, Mark, back to you. How will Hager's EMC system be connected, if at all, to smart meter gateway CLS boxes?
So we can connect the EMC to the smart meter gateway using EEBUS, for example. But this is depending on countries. EBUS is today EBUS is it's, let's say, very popular in Germany, and we try to expand this, because for us as manufacturer, we don't want to have 100 different protocols to implement in our devices, because at the end it's R&D, it's complication. So if EBUS could be the one, it would be perfect, because it's simpler for us. We have to do the job only one time, and not having for each country, because this is depending on the country, because the EMC is in the building, so it follows the country rules. And also from one country to the other one, you don't have the same metering systems, you don't have the same DSO, and so on. Today it's very country driven, this business. So the smart meter gateway is a German device, and its main function is a firewall, and it's to protect the grid from pirate attacks, because they have the fear of a global shutdown because of hacking. In fact, you could shut down 100,000 houses at the same time, and they fear of this, and that's why we have this smart meter gateway. That's the way Germany has chosen to do it. Other countries have electronic meters where they integrate this feature, so they have different way to do this. What our opinion is if we find universal protocols that are speaking the language between the different devices, it will be easier and simpler for us, and also you have also interoperability that is guaranteed.
Yeah. We are getting in some questions. Sanna, there's a small question for you. I hope you're on the line. And that question is, related to Smart Otanyemi. So is there at the moment any plans for any type of collaboration between the Smart Otanyemi ecosystem and the EBUS Consortium?
Thanks, Sami. Very good question. I think we could maybe move on to the next slide, perhaps, because there will be
definitely.
an answer to this. So first of all, big thanks for the very informative and interesting presentations, Niklas and Mark. We have now heard what EBUS is and got a snapshot of best practices. If you would like to continue exploring the opportunities of EBUS more and maybe enter to the piloting it at Smart Otaniemi, let us know your interest and we will gather the team for the next workshop session in May. We are also eager to hear insights, feedback, comments regarding EBUS Initiative, so feel free to give those to us afterwards. And how this works in practice. We will send you the webinar materials by email soon, and in the email you will find a link to the online form that you can fill and send your feedback and register to the next workshop.
Thank you, Sanna. That was wonderful. And we will be showing some links to you also on that. But before we end or conclude, we still have time for a couple of questions if you would like to send us in any. Mark and Niklas, this one is perhaps for both of you in a certain way. You have talked about EBUS, and I think EBUS, we are seeing it as getting into a global standard. And then, at some point in time, I don't know when that would be, but do you even see the potential of let's say, energy trading almost in real time across countries? So again, decisions not necessarily made at a national level, but by building owners or facility owners, etc.
Definitely, I see see that in the future, but at the end, this is outside of the scope of EBUS. Because what EBUS is doing, it enables the access to the single resources in the building, the transparency between the building and the grid. But as said, it's an enable. It's not excluding these border crossing solutions that takes advantage of this interoperability.
Yeah.
It's the same for Hager. We are technical enabler. And if someone DSO or others want to operate this, it will be feasible in the future using this smart and communicating systems.
Very good. Thank you all very much for joining us, and I'll pass over now to Sanna to talk a bit more about some links on Smart Otanyemi, and then to give us a couple of closing words. Thank you for joining us, and if at any time you would like some more information, like Sanna told you before, and I'm sure she'll repeat it, do go to the website, fill in the form, send us feedback, and if you want to know more about both EBUS or Smart Otanyemi, and of course, if you'd like to hear any future webinars from us. So that's thank you from my behalf, and Sanna, back to you, and let's hear about how we join the Smart Otanyemi movement.
Thank you, Sami. So here we remind on Smart Otanyemi contact channels, smartotanyemi.fi, hashtag Smart Otanyemi at Twitter and LinkedIn, and our email address smartotanyemi@vtt.fi. Please don't hesitate to contact us in any questions or ideas related to EBUS or any other smart energy topics you are keen to. And last slide, please, Sami.
Here it comes, of course. Thank you, Sanna.
So on Smart Otanyemi team's behalf, I thank you all participants and wish you all the best. Take care, stay safe, and be in touch. Thanks and bye.